Hello and welcome to Mellow Labs. On today's episode, hold on, this is still loaded. This is my hot glue gun. I'm not affiliated with the Neon Green gang, it's just what I've ended up with, and quite honestly, it does the job. You put the hot glue in, you put the battery in, you turn it on, and then like 8 minutes later, you can dispense as much hot glue as you'd like. The problems start when you need to dispense a lower temperature hot glue for a long amount of time. Like for example, putting up 856 individual LEDs to show your Patreons you love them. The process is quite simple. You put down a little bit of hot glue and then you place an LED on it, holding it down with your finger until it solidifies, and hopefully the hot glue isn't hot enough to actually burn you. And then you keep doing that, and all whilst turning the hot glue gun on and off to keep it in the Goldilocks zone, sometimes overshooting it, burning your finger, and sometimes forgetting to turn it back on and having to wait for it to heat back up. And after doing that for many hours during a live stream, I realized, wait, my entire thing is making things smart. So today, we're making my hot glue gun smart, but without Wi-Fi, so it's somewhat smart. Right after this message from today's sponsor. Today's episode is brought to you by JLCPCB. JLCPCB offers easy, affordable and reliable PCB and PCBA services. Simply upload your Gerber files to jlcpcb.com and get an instant quote. 1 to 8 layer PCBs start from just $2, and right now there's a special deal for 6 layer PCBs where you can get a $30 coupon which brings down the price of the 6 layer PCBs to just $5, and they'll even include an ENIG finish and no engineering fee for Virin pad. And if you're worried about quality, just don't. JLCPCB owns 5 state-of-the-art factories with quality control at every step, and if you need your boards right away, JLCPCB offers a lightning fast 24-hour turnaround time. So sign up with the link in my description to get $70 in new user coupons, and thank you again to JLCPCB for sponsoring this episode. I started by disassembling the hot glue gun, and once I was inside I made sure to take very clear close-ups of where everything goes, because this hot glue gun is probably going to stay disassembled on my desk for multiple days, and like hell I'm going to remember where everything goes. So always record your work, it saves your butt in the future. After that, I continued disassembling it, and I could have actually disassembled it even further. Like I could have removed the silicon bit off of the heater module and the nozzle unscrews, but that didn't seem necessary at all, so I just continued until I had all the electronics in my hands. The next thing I needed to figure out was what this little PCB actually does. I had a look online for the little IC that's on it, but I couldn't find any specific data sheet for it. It does seem to be very closely related to some generic battery protection circuits, so I assume that's what that is. In that case, I needed to figure out what the voltage range of this IC actually is. So I plugged it into my bench power supply and my multimeter, and I started by giving it 18 volts, which is the battery voltage, and then I slowly started to decrease the voltage until the IC cut off, as indicated by the little red LED, and that seems to be around 15.5 volts, and I can turn it back on, and then it turns on for a second and then turns back off. So that's how I know that that's the limit. Anything above that, it stays on and continues powering the heater. I also wanted to find out what the upper limit was, but I didn't push it too far beyond 20 volts because I didn't want to break the hot glue gun and then have to buy another one for this project. The last thing I needed to know is how much current it actually pulls. So I set my bench power supply to 20 volts and then I checked my bench power supply and it said it was pulling around 4 amps. So just to be on the safe side, I'm gonna call it 5 amp. So that's all the investigating I needed to do on the internals. So now let's figure out a plan. I made myself a new whiteboard. I really missed being able to like physically write things down. I'm so happy with it. This is the current layout of the hot glue gun. We've got the battery, which goes through the switch into the battery protection circuit, which basically just cuts off the battery when it drops below like 15.5-ish volts. Anything above that, it just dumps it right into the heater. It does step it down a little bit just for the little LED, but apart from that, if it's on and there's power, it dumps it into the heater. So my idea is to kind of just be able to turn off and on the heater with either like a relay or a MOSFET, depending which one I choose. I'm either going to go with the bang bang approach or PID. I'm not going to lie, being able to say that I PID tuned my hot glue gun is kind of a flex, so I'm kind of leaning towards PID. Hello. So I realized that I didn't elaborate on the two methods like at all, so let me explain. Bang bang is very simple. It just turns the heater on and off depending on the threshold. So if it's above the threshold, it turns off. If it's below the threshold, it turns on. Bang, bang, very simple. But you end up having a lot of temperature deviation in between the bang bangs. PID control, on the other hand, is a bit more involved, but instead of just turning it on and off, it's constantly adjusting how hard the system is working, looking at like how far away it is from the set point, how quickly things are changing, and how long it's been off for, which lets it start slowing down the closer it gets to the set point, which in turn lets it be a lot more accurate with holding the correct temperature without drifting too cold or too hot like this guy. So now that you know that, we can continue with the video. I'm gonna need to control it with like an MCU. I haven't decided what yet, but whatever is smallest and already in my inventory is probably what I'm gonna go with. I'm also going to need some kind of thermistor so that I can actually check the temperature of the heating element. And for the like user interface part, I've got a couple of like these little OLED screens. I think they're like 0.91 inches or something silly like that. And I'm thinking just like a rotary encoder so that I can actually input what temperature I want. And the very last thing I need is some kind of, I think, buck converter so that I can actually step down whatever voltage we're getting from the battery down to a reasonable 5 volts for all of this stuff. And I think the best place for me to actually snatch power from will be just before it goes to the heating element, because that's after the battery protection circuit. So if it cuts off, this should cut off too, so that we're not actually letting the battery drain even further. So that is pretty much my entire plan. Now I need to figure out what relay or MOSFET I'm using here. I have a couple in stock, but nothing that will be sufficient for these kinds of loads. And what back boost converter I'm using. I have one that I think will work, but I want to test it first before actually implementing stuff. All the other things I think I have. So let's do some research. Sometimes my job is fun and rewarding. Other times I have to scroll DigiKey for about 3.5 hours trying to find the perfect MOSFET. Luckily, it didn't actually take that long. I went to DigiKey, I filled in all of the traits that I want my MOSFET to have, and then I scrolled through the seemingly never-ending list of MOSFETs that DigiKey has to offer, and I picked out this one. Ignore the fact that it's no longer manufactured, you can still pick them up on eBay. It can handle 60 volts at 32 amps, way more than we need, and we can drive it with 5 to 10 volts, but we will be driving it with 3.3 volts from a GPI open, so it's still going to work, it's just going to be less efficient, generating a little bit more heat. So then I went on eBay and I found a pack of 20 for £12.10. I'm sure you can get them cheaper on AliExpress, but they had a 3-day delivery period, and I want these kind of fast because I get bored of projects very quickly if I don't have all of the parts. So I've already ordered them. They should be arriving in the next few days. So meanwhile, let's do something else. Okay, so to step down the voltage from the battery to the low voltage electronics, I'm going to be using this little guy. It's a step down converter based on the PM1584. They're very popular. You can get 10 of these for like £5 on AliExpress. They can take an input voltage of anywhere from like 5 volts to 28 volts, and you can output 0.8 to 18 volts. And you can do that at like 3 amps with, I think, a peak of 4. So way more power than we actually need for these electronics. But I want to test this out and make sure that it's actually configured for 5 volts. So I'm going to connect it to this multimeter, which will show you the voltage I'm putting into the module. And this multimeter will show you the voltage coming out of it. I'm going to set my bench power supply to the lowest voltage we'll be getting from the battery, which should be like 15 volts, about there. And we can now turn this little potentiometer on here to actually set 5 volts as an output. Oh no, I've got my multimeter in the wrong mode. Okay, this multimeter is horrible, but it just about does the job. So now I can increase the voltage to what is going to be the highest voltage we get from the battery, which will be around 20-ish volts, and we should still have 5 volts on the multimeter here. So that seems pretty good. So if I do a whole sweep of the range from the battery, we should have nothing but a steady voltage of 5 volts coming out this side. And that seems to be what I'm getting. Nice, so this is gonna work beautifully. Right, let's move on. Okay, so I think I've gathered all of the components I need for the rest of this project. And first of all, I've changed my mind slightly. I know I said I was going to use one of these rotary encoders to actually input the temperature and navigate menus and things like that, but these are quite big and bulky and I want this to be like somewhat sleek and out of the way. So instead, I'm taking inspiration from my TS100 soldering iron, which uses just 2 buttons for all of its navigation, and I'm not going to have as many menus as this soldering iron does, so 2 buttons is going to be more than enough for me. So I'm going to use 2 of these 6x6mm push buttons for all of my navigation. To actually tell me the temperatures and things like that, I'm going to use one of these tiny I2C OLED displays. I've used them for a couple of things in the past and they work pretty reliably, and they are 0.91 inches. So yeah, pretty small, pretty reliable. I recommend them. For the actual processing, I'm going to use this absolutely adorable RP2040, which is basically just a tiny version of the Raspberry Pi Pico, just a lot smaller and a lot cuter, and it doesn't have quite as many GPI opens, but I don't need all of them anyway, so this is going to be perfect. But I don't want to solder on pins just so I can test with it, so instead I'm going to be doing my testing with this Raspberry Pi Pico W, because it's already got pins soldered on and it's on a breadboard. Now for the actual temperature measurements, I'm going to use this thermistor that I had laying around. I think I scavenged it during one of my Disassembly live streams, but I have no idea what its former life was, and I have no idea if it works. It's called a tube thermistor because it's a thermistor inside of a tube, and apparently all I need to make it work with my Raspberry Pi Pico is a 10K resistor, which I have, but the last time I ordered them I selected the wrong size, so all I have is these giant 10K resistors. It's going to do the job just as well, it's just comical to look at in comparison to all the other components. So I'm going to try to get this to work with the Raspberry Pi Pico and see if this thermistor actually works. Okay, so I've got it connected and it's currently printing out the temperatures in the terminal, and it seems to be working, but you know, we've got to give it a good test. Yep, okay, 107, 117, 120. Yeah, I think that works, just to be sure. 204, 207, 215. Yeah, that definitely works. Okay, awesome. So now I'm going to add the display so that we can actually see the temperature without me having to look over at my desktop. And whilst we're at it, we might as well add the buttons. Maybe we can use them to like flip through the different temperature types, like Celsius and Fahrenheit and Kelvin, and I'm sure there's other ones. So let me wire those in and I'll be right back. Everything is wired up. I uploaded a new script, so now on the screen we have the temperature coming from the probe, and I can also switch between the different temperature readings. So we've got Celsius, Kelvin and Fahrenheit. So now I can show the Americans how hot this is. It's that many Fahrenheit hot. My next step is to actually test this with the MOSFET, but they haven't arrived yet, so we might just have to wait a little bit. For you, it's going to be quick. For me, it might be days. So I'll let you know when they arrive. I'll just be here waiting, all by myself in a room. I should really get some friends. Good news! My metal oxide semiconductor field effect transistors have arrived. All 20 of them. Yes, I know there isn't 20 of them here because I've decided to save you a Mellow Labs transition, and I've already put one on a breadboard. And accidentally burnt 2 of them, but we don't speak of the sacrifices. Connecting it all together was actually really simple. I followed this diagram that I found on the internet, and all you need is the transistor and the 10K resistor, and you're good to go. So now I'm going to connect this to my lab bench power supply. I'm only giving it 9 volts for now because all I'm doing is spinning up this motor. So now if I bring over my Raspberry Pi Pico board and connect this cable to ground so that these have a shared ground between them, and now I can tap this little guy on the 3.3 volt pin, which will spin the motor like so, and if I take it off, it stops. I've also slightly reprogrammed the script, so if I plug this into GPIO 14 here and grab the thermistor along with my hot air gun, and I bring up the temperature, and the motor should start spinning when it goes above 100 degrees. Oh, there it goes. So the way it works is I'm controlling the MOSFET with PWM from the Pico, and the higher the temperature, the faster the motor goes, all the way up to 120. So if I put heat on this tube thermistor, when it goes above 100, the motor should start spinning, and it should go a lot faster as well. And when it gets to about 120, that's as fast as it can go. So I can then just let go of the heat again, and it should start ramping down. Just like that. So that works pretty much exactly as intended. So my next steps are to start making things a little more permanent. The first thing I'm going to start with is making the user interface part a little prettier and on a prototype PCB board so that we can actually have it outside of the hot glue gun, and then we'll do all the other bits. Okay, so it's been many hours of very fiddly work, but I can finally see the finish line ahead of me. So let me catch you up with everything I've done. Firstly, on the side here, we've got this little interface board with the buttons and the OLED on a nice little prototype PCB board, and it's all nice and condensed. There are 6 wires going into the hot glue gun from there. And don't worry, I'm not planning to just leave this floppy like this. I'm planning to glue this down and get a 3D printed shell over the top of it. So now let's move on to the inside of the hot glue gun, which is where, oh boy, there's a lot going on here, and I'm not entirely convinced that the second half of the enclosure is going to close without giving me a whole bunch of fuss, but at this point I'm willing to cut off any piece of plastic that stands in my way of closing this. But we'll get to that later. Let's start from the top. To the actual heater, the only thing I had to attach was the thermometer, and I did that using some twisted wire and a little bit of super glue. I wish I had some kind of like thermal epoxy or something like that, but I didn't. So super glue is gonna have to do the job for now until it eventually fails and I have to go in here and repair it. But for now it's gonna do fine. And we can now swiftly move down to what I call the wire canyon. There are 12 wires here trying to go through a very narrow passage, and somehow they are doing it. There are little clips that are designed to hold the wires in place, but I think they're intended for the original 4 wires, not 12, so the wires keep popping out of them and jumping out. Luckily, this doesn't seem to have caused any problem for the actual trigger because it's moving back and forth almost unaffected. And now I have the pleasure of trying to explain this absolute rat's nest to you. And I like to think of it as a burger. There are layers to it, so let's start from the bottom. At the very bottom, under this PCB, is the actual MOSFET that controls the heater, and it's wrapped in some heat shrink tubing to stop it from short-circuiting everything. And then that's held in place by the actual PCB that cuts out the battery when it goes too low. And then we've got the Pico and the buck converter, and the idea is that all of these kind of just stack up on top of each other and fit into the enclosure without causing problems. And yes, I will add some kind of tape or something to stop them shorting out on each other as well, but I'll get to that. My next step is to actually write some code, because I really tried getting this Pico in a position where I can still plug it in after the fact, but I can't do that. So I have to upload the code and everything before doing that. So the first script I need to make is one that actually like runs a couple of heating cycles and figures out the like inertia and heating and cooling of this system, so that I actually have the PID values that I can then put into my main script. So let's do that. Okay, so it's not actually particularly interesting to look at, but I ran the auto-tuning script, and it basically just did a bunch of cycles of heating and cooling, and then figures out what the best values are for your particular situation. In my case, it gave me a few different ones that I could choose from, and I picked the most aggressive values, mostly because I want the hot glue gun to heat up quick. So that's what it's going to do. It's going to heat up quick, overshoot a little bit, and then, you know, accurately level itself off. So I put all those values into my main script, and we are now ready to close this hot glue gun. But just before I do that, I actually need to put something in between these circuit boards so that it doesn't actually short out. So I think I'm going to go with the best insulating material, a neon green sticky note because it kind of matches the hot glue gun, so it feels like it's gonna work. I don't remember if I mentioned this earlier, but to save some space, instead of using those giant 10K resistors that I had, I instead opted to use some surface mount 10K resistors that I had with some wire soldered to them so that it actually doesn't take up any space at all. Okay, moment of truth. Will the case fit back on? Oh, nowhere near. Holy crap, it fit. I mean, it's very tight, but it fit. I need to get those screws in before this decides it no longer wants to fit. I am actually bewildered that it all fit inside and nothing seems to be broken. Let's test it out. Battery on. Okay, it should be heating. According to this icon, it's heating. That's the temperature we're trying to reach, and that's the current temperature, and it's going up. Sorry, so is my voice apparently. It's actually working. I made an actually useful thing. And I can adjust the temperature. So if I go, I actually feel like having 130 degrees. Bang, done. It's weird to say that I'm finally proud of something I've made. Well, it's not finished yet because I still need to 3D print the thing that goes on top of here. But like, this is actually something I'm gonna use probably often. I'm actually gonna heat it up to 170 and see if I can just fully press the trigger without it, you know, getting jammed or blocked or anything. There is a slight problem with the way I did this, mostly because I'm not actually measuring the temperature of the hot glue itself, but of the thing that heats the hot glue. So that's obviously going to heat up a lot quicker than the glue inside of it. And then the heat is gonna like permeate inside of the hot glue. But it works. So can I, oh yeah, I have the full range of the trigger. This is amazing. All this time, I have been making random things that don't make sense. And now I've finally used all of that knowledge to make something useful. I'm turning it off and I'm jumping into CAD so that I can actually make the thing. I'm so happy. I made a thing that works. A couple hours of 3D modeling and 3D printing later, I have a bunch of test prints that are all very slightly different. It's mostly just making sure that the buttons and the screen are all perfectly aligned. But then I went and printed it in, I believe this is like apple green PLA, which is not a perfect match for the hot glue gun, but it's good enough. So I should be able to just pop that on. Okay, you know what? I don't want to be the person who like toots his own horn, but look at that. That looks so good. Like it doesn't blend in perfectly, but it also doesn't stick out like a sore thumb, right? That's so nice. And the fact that this is going to be something that I'm actually going to use like on a not daily basis, but often is so nice. And I can have different like temperature presets. I know there's like a whole bunch of different like hot glues as well. There's different colors and probably different materials and stuff like that. So I can like find the perfect temperatures for whatever task I'm working on. Oh, this is gonna be so nice. I just realized I could very easily make this into like an upgrade kit. Like all I would need is like a PCB board that's about the same-ish size as the original board that's in here, maybe a little bit bigger because I need to put more stuff on it, but it would have like the battery protection, the Pico and everything else, and then all you'd have to do is run a ribbon cable up to the display and the thermistor so that we can tell the temperature, and like that would be like almost it. That would be so doable. If that's something you'd be interested in, let me know down in the comments below. And I guess with that, thank you very much for watching. Don't forget to like and subscribe. Support me on Patreon if you can. And I'll see you in the next episode. Goodbye. Jesus Christ, it's Jason Bourne. Dun, 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 dun.